There is a bit of a wrench in this one that many people miss. It won't actually affect. Well, I guess depending if you miss the RA on this one, it does, or it won't affect. But if you miss the OA for the Fe2+, it could affect. Okay. Jamie, which one is the strongest oxidizing agent? The copper ion or the copper solid? Okay, so the copper ion is the strongest oxidizing agent. The strongest reducing agent is the iron solid. Better than anything else. And this board is going to drive me nuts real quick. Oh wait, I already have nuts. So we are going to write the reduction half reaction. I'm going to write the oxidation half reaction. And I'm going to write 2 electron slot gain, 2 lost. I'm going to write the net ionic reaction. Okay. Now, which one of these reactions happens at the cathode? Which one of these half reactions happens at the cathode? What happens at the cathode? Do electrons go towards the cathode or do electrons leave the cathode? Electrons go towards the cathode. The reduction half reaction occurs at the cathode. The oxidation half reaction occurs at the anode. Okay. So we now know the direction of ion flow because we need to gain electrons at the cathode. I'll be right there. Actually, I gave this. Do you have the notes from Tuesday, Kyle? Because I did give the notes Tuesday. Yeah, it's on the back of that. Okay, so the electron flow goes from the iron anode to the copper cathode. The electrodes are the solid bits in the metal, or in the half cells. Yes, it's the copper 2 that's reacting, but it's the copper metal, the copper solid, that is the electrode. or in this case, the cathode. Okay? So we have our cathode half reaction, also called our reduction half reaction. You have your anode half reaction, also called our oxidation. This is the net cell potential, or the net cell reaction. Now, we want to know which ones are negatives, anode or anions or cations. Anions are negative. Since the negative charges are flowing in this direction, the remaining negative charges must be flowing to complete the circuit. Because if I don't have the anions flowing that way, I have a buildup of extra negatives over here, and I don't like that. And the cations are going to go in the opposite direction. There are 3 empirical observations that can be made as this reaction takes place. 3 things that you can observe if you let this reaction go long enough, besides a light bulb lighting up. What are some indications of progress as this reaction takes place? We started with aqueous copper ions, and we ended up with copper solid. So the cathode, the copper cathode, gains mass. We're taking copper ions, which were floating in solution, and they're going to end up on the copper electrode. We have iron, solid iron becoming iron ions. So what's happening to that iron cathode, or iron anode, I should say? Losing mass. Now, if it happens, that's not true. In a lot of cases, the cathode will gain mass and the anode will lose mass. Not every case, depending upon what the anode, what the cathode is. There is one other thing that you can see as this reaction takes place. Go to the back of your data booklet and tell me what the color is of copper 2 ions. So copper 2 ions are in solution are blue. That was kind of what I showed you yesterday. So I'm using up the things that cause the blue color. What's going to happen to the color? It's going to decrease. Now we'll say it this way: the blue solution at the cathode becomes less intense. So instead of saying it, we just say the color becomes less blue or less intense. And that's, now, does this happen automatic or right away? No, it happens over time. What's eventually going to happen if you let this battery run long enough? You're going to run out of the iron anode. You're going to lose up all that iron anode, and you're going to use up all this copper 2 solution. So when the battery in our calculators run down, you've either used up all of the anode, or more likely used up all of the ions at the cathode. Now the same principle applies to our phone. I have done some research into what happens with the phone, but I can't tie it directly into this. But it's the same principle. Electricity makes our lives a lot easier. Okay, so does that You guys have an understanding of that? Now, what happens? What happens when we have something that does not have a metal in its half reaction? The dichromate or the hydrogen half cell. So the dichromate half cell would have the dichromate ion, the hydrogen ion, plus, I think it's 6 electrons. Okay, so this one don't bother writing it down. I don't need to worry about it. But there's no metal to become an electrode in this case. Or the same thing would be for this half reaction. There is no metal. There's no solid. What do we do? There's a couple cases like that. The lead sulfate battery is one. But what we do is we use what's called an inert electrode. Basically, a carbon or platinum electrode that allows the reaction to take place on the it. Just like with the one back here. Here we had reactions taking place on the copper, and the reaction included the iron anode. We need a place for that reaction to happen. So we are going to deal with a carbon or platinum electrode. And this is a carbon electrode. Now, one of the reasons we use carbon and platinum is they have a really, really good hold on their electron. Carbon does not form ions. It does not give up its electrons at all. Platinum takes a lot of work to give up its iron or its electrons. We could also use gold. Yeah, we're not using gold. Platinum is expensive enough. So all it does is allows the reaction to take place on it, allows the electrons to flow into it from the wire, the electrons to go into solution, or on the other side, it allows the electrons to come out of solution if that is the case. So here we have our half cell notation. Chloe, what does this double line mean? Okay. Basically, this is standing in for our salt bridge. Okay, so that means we have the ability for ions to flow between. These single lines means just that we've got these electrodes in this solution, or these solutions. So we've got this guy, 1/2 cell, 2 beakers. That salt bridge is indicated by that double line, and then I've got my 2 electrodes in there. Okay, this is how we read our cell notation. So carbon, don't ever bother looking for carbon on your booklet. It doesn't exist on our booklet. We have this guy being an SOA. Yes, we have the hydrogen being an OA, but the dichromate is stronger. We know this is our NOA, and this is an RA. Okay. So to answer all of these questions, I really stress that you do the 5-step process. What is the anode? What is the cathode? What is the direction of flow? Our SRA is our copper. think that's the equation for the dichromate half cell. And for our copper solid becoming copper 2 plus and 2 electrons. Now, do you have to complete the 5-step process to answer all those questions? No. What you have is you've got the reduction half reaction and the oxidation half reaction. The reduction half reaction happens at the cathode. So the carbon is the cathode. The cathode half cell is everything here, but the cathode is the electrode, the solid bit that it goes into the solution. The carbon or the copper is the anode. And now I can answer everything else. We've answered the cathode, the anode. The electrons are going to flow that way towards the cathode because we need to have them there. Your question? No, the cathode itself is the carbon solid. It is the solid part. Yes, this is what's happening at that solid electrode, but that guy's our electrode, our cathode. So the cathode half cell, that side, but the cathode is the solid bit in it. Okay? So the cathode does not have to be involved in the reaction. It just has to be there, near the reaction. So electrons going this way. What flows in that direction? Anode or anions or cations? Yep. Negative charges complete the circuit. We have a buildup of negatives over here, so we have to get rid of them. So in this case, the nitrate or whatever we made it up of would be flowing that way. And you have a buildup of positive charges because you've taken away a negatives to put them in the electrons. The negatives flow that direction. Now, before we go, I'm going to ask you to do one more without my help. Yes. Oh, you mean, can you, generally, they'd be flowing that way. Yes, it can, because all I have to do is swap them around. There is a convention to write this, and I think it's writing the cathode on this side, but I don't know. I just happen to have always written the cathode on that side. Always flow towards the cathode, whichever side of the cell it's on. Cathode is always with the strongest oxidizing agent. Right? So what's happening on the cathode? Reduction, gain of electrons happening on the cathode. Okay? Okay, so I want you to make sure I put everything on here. I want you to identify the cathode, the anode, and the direction of electron flow, the direction of ion flow, and two measurable quantities that you three measurable or observable things that you would see other than a light bulb lighting up. And I am going to put a wire between these guys. So they are connected. It's just, I'm asking you to basically interpret a really crappy drawing. Yeah. Yes. So you had H on the left-hand, right-hand side, you would have H2, H plus, and NO3 negative. All right, I'm going, yeah, okay, never mind. We'll leave it as it is. I kind of messed up a bit. What's that? Not in, other that one place, that's an hour.
Which are your drugs? But looking at what we have training salt in a solution from the plus separated by the salt solution. Anyway, we have carbon salt. So that cell location corresponds to negative traffic drop. This is a spectator. This guy isn't always. This guy isn't always. Now I see that. Hold on. Here's one mistake. This is the right order. What's our strong?
And it's not all.
Like that. They're choosing what? Oh, yeah, so electrons and ions got one. So good. So now, perfect. Now, which way are the electrons? Here. Is that two? I'm glad you made that mistake to remind you to talk. The electrons are flowing this way. Which way are your anions flowing? So which way are yes, you're right. It should be on any on.
Okay, walking around, I don't see any concerns. I do see one thing that is a mistake that I want to fix. Because I see this too often. C2. Okay. What are the diatomic elements? There is a Finchbo. There is a C in Finchbo. But that C stands for which element? Yep. And the person who made the mistake, it's not the first time I've seen it. Okay, so fluorine, iodine, nitrogen, chlorine, hydrogen, bromine, oxygen. You do have to have those. It's a minor error, but please don't make that anymore. So you do have those questions to work on. Page 626, 6 questions.